Again, this will sound a little abstract, so we'll just take one numerical example, not numerical, one example to narrow to understand this better. Okay. So example, what is the rate of convergence? Let's work this out. Of the sequence xk is equal to 1 by k factorial. So I'm giving you a sequence, right? The first term is 1, then 1 by 2, and then 1 by 6, and so on, k factorial. So what is x star for this sequence? 0. Very intuitively, it's clear that x star is equal to 0, right? Okay. So let's take our, so in this case, it's a scalar sequence, not a vector sequence, so I don't need norm. So if I take, for example, xk plus 1 by xk, what am I going to get? 1 by k plus 1, right? Now 1 by k plus 1, does it, what can I say? Look at the definitions. 1 by k plus 1, as k tends to infinity tends to 0, right? So this is super linear, right? Okay. Can it also be quadratic? I mean, we found this, it is satisfied super linear, but is it also quadratic? Let's just check. So I take xk plus 1 divided by xk squared. What am I going to get? K factorial divided by k plus 1. What is this limit as k tends to infinity, or for large k? Infinity. It's not going to a positive number. It's not, for example, here it is not being upper bounded by some constant number, right? So this is actually infinity as k increases, right? So therefore this sequence does not have quadratic rate of convergence, it has superlinear rate of convergence. You will find always that it's going to be only one of, it's not going to be both at the same time. Okay. So this is an example over here. Okay. So we've spent time talking about linear algebra, we've spent time talking about analysis. The next thing that I want to talk about is going to be about convexity, which is important part within analysis. So let us see, how are we doing on time? I think we're out of time, so I'll give it a pause over here. Okay, so we will start with, yes, question. What about linear? Okay, so let's see, what about linear over here? So when I take this ratio over here, yeah, is it linear or not? For large k, what is happening? 1 upon k plus 1. If I take k very, very large, notice it's a very subtle point. Is there a restriction on R? It's between 0 and 1, yes, but little bit more specific than that. Is it a closed interval 0, 1 or an open interval? It's an open interval. That means 0 is not included in that. So if it just says for all large k, if I take k to be arbitrarily large, R will actually tend to 0. So it slips out of linear and goes into superlinear, right? For linear, you will want that R to be a strictly positive number, and 1 by k factorial is not, okay? So it's a subtle point, but that's why this is very crucial, that it is an open interval 0 to 1. Yeah. R can still be less than 0.5. Yeah. Right. That is one way of looking at it, but the comprehensive way is that if it is satisfying a higher definition, I declare it to have that convergence. Okay. Yeah. No. If it is Q quadratic, it is you say it has quadratic rate of convergence. Okay. you declare the higher one. From a practical point of view, that is what you are interested in, right? So quadratic will of course be as fast as linear, but it's much faster than linear. That's the sense in which we will use it. Okay, so let's let me just go over what we've looked at, right? So we started with this review of linear algebra. Now, those of you who have not taken linear algebra can, after this class, take a call about how comfortable you feel with linear algebra, right? Vector norms, matrix norms, fundamental subspaces, eigenvalue decomposition, singular value decomposition, something about convergence of a sequence, definitions of upper bounds, and rate of convergence. These are some of the things that we have looked at. All of this is in the class notes on the website. So please do have a look at it and let me know if you spot typos. I'm sure there are lots of typos. So let me know, please. Yeah. Well, you can, okay, so how I calculated in the case of the student, how I gave him this number of 3 times the age of the universe is that it was a combinatorial problem. There were 100 possibilities. I mean, there was the variable of optimization was of length 100. Each of the vector, each of the components had 2 options or 3 options, 0, 1 and 2 or something like that. So you can think of how many possible 3 to the power 100. Okay. Then you can say I'm using an Intel Core i9, whatever. One calculation, let us say, takes 1 microsecond or whatever. One iteration takes that much time to evaluate is that a good solution or not. And then you just multiply it out together and you get age of universe. Right? So many times you can do these things just by plain back of the envelope calculations. It's not always possible. Here it was possible because I knew that this is the exhaustive list. The solution is sitting somewhere in that, right? So you can calculate, but usually it may not be possible. Yeah, because the algorithm was brute force. So you can hand the chit to any of us and head out. Yeah, question? Yeah.
We have some rectangular matrix.
Right.
I mean, at least from what I know is like we take the product of A and A transpose.
Right.
A transpose is A.
Right.
We get the eigen decomposer.
Correct.
We get the left eigenvector matrix, right eigenvector
Right.
matrix, and the singular values.
Right.
But why is it true that A is also equal to U epsilon V transpose? Like we know U, we know epsilon, we know V. How is the proof coming? Like from where?
Oh, from where do you get the proof? It's a constructive proof. If you want, so if you look at my course website for the linear algebra, there is a proof for how you come up with the SVD, the decomposition, starting with exactly what you said. So it's not something I can tell you in one sentence. You build it up step by step and you do it exactly like that. You form A transpose A, A transpose, and you factorize it. There is something called the Schur decomposition. That's a very important theorem that is used. The Schur decomposition is used to convert the EVD into an SVD. So it's an involved proof. It's not very easy, which is why most starting linear algebra courses don't give you the proof. They'll just say, here is decomposition, be happy. Question? Yeah. 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 A inverse. The condition number will be the same. So condition number you can think of as an amplifying factor. So if to begin with, if B has small amount of noise, the amplification will result into a, let's say, a reasonable amount of noise. But if B has much more noise, then the amplification factor is the same. It only depends on A. It tells you the amplification factor. So it's a relative quantity. You have to know what is the noise in B so that you know that actually how much noise are you going to get. And actually, I skipped one detail. You can have noise in A also, right? So there is a lengthy. There could be how you modeling error in A, for example. Modeling error can give you an error in A. So this condition number captures a lot of these things. So people who do numerical analysis are very particular about condition number. Something like that. Right. Right. So then we take superlinear. We go for the higher order.